So what I'm going to show you now is using an Arduino UNO to directly drive a display like this. Like I said, I'm showing you these devices, which is nice from ynvisible, but I also am trying to show you a level of coding for this as well. So you can see here, this is what I had modified from the original one, which was provided to us, which is right here. So you can see they just had this one thing for the 2-digit display. I've changed it so that it works with 3 different types of display, just simple if-defs and things like that. Now we're going to go and look at the code using a different Arduino. It's still an Arduino UNO, but it's not the Elegoo one. It's a genuine Arduino branded one, and we're going to drive it directly. So let's get rid of this one. So hopefully you can see the display there. See if I can get rid of some of the glare a little bit. So we have an Arduino UNO. We have a breadboard which just patches out from the data lines to the breadboard, and it just jumps out to the display adapter. And then I have 5 volts coming across. I have 2 10K resistors, dividing the 5 volts down to a split rail of 2.5 volts, which I'm using as the common of the display, which means any output that I take to a positive state will be at 5 volts, i.e. plus 2.5, and any output that I take to a 0 volt will be minus 2.5 relative to the common of the display, which should be enough to drive this display. If I was using a 3.3 volt microcontroller, I would have the common rail stuck to one of the outputs and I would just invert it. So we would truly get plus 3 volts or minus 3 volts on the segments. This should be good enough to demonstrate what I'm talking about though. So let me just bring the code up here. That's our old code. Here we go. So first one I've got up here is the original code we were looking at a week or so ago, where we defined all of the pins. We defined digits on and offs and things like that for use in the code to make it easy to remember. We got the 4 segments, and then when we wanted to set a letter up, we had to initialize all the outputs, all these individual statements, and then we would output which digit we wanted on, and then we would tell it individually which pins to turn on. Now, this works well in an environment like this, and it's easy to understand, but it's not very fast. I'll do a separate video on getting major performance improvements out of an Arduino or an ATMEGA 328. I'll also be defining what is really meant by Arduino as well. So each digit we change, you've got all of these statements here, and then you've got a whole bunch of other statements for the next one, then the next, and then the next, right? So we want to simplify this. Now I've already just put together a bit of code and saved it, so let me just open it up. There we go. I need to shut the other one because it's probably going to share the pin. So here we've got the same beginning of the code, but what I've got now is 2 delays because remember I mentioned at the very beginning of the video, when we write to this display, when we write to these displays, we really need to make sure we only bring on the differential voltage for a fixed period of time rather than leaving it there. Otherwise you'll prematurely age the displays. Instead of having individual bit patterns now, going back to the code here, instead of having individual bit patterns being written as individual pin writes, I've defined all of the letters from 0 through 9 as a binary value. Okay, now you can find examples of these all over the place on the internet. If you look, you can copy this too. So it's a 10 bit, it's a 10 byte array, and each byte represents the character. So you can see byte 0 is all of the segments on, 1 means on, and then the G, which is the one in the middle, is off, and the decimal point is off. This includes the decimal point. So they're just defined into an array to make it easy to access. And then down here, I've left the defines in. Oh, actually, I've changed the ints for the pins to defines. The nice thing about that is they don't take up any memory. The second thing is when you reference it, it doesn't have to go and read from a memory location to get the value for a specific variable, pin A, pin B, pin C, pin D, etc., and then go and do the I/O routine. By using a define, it effectively sets up a virtual value, and that value gets injected directly at compile time rather than have to go get it. So technically it's faster, and it probably is a little shorter as well in code length. I've got a little bit of serial I/O set up just so that I could do some debugging when I was checking this. Now the first thing you're going to notice here is how much shorter the initialization is. These two statements here are doing the exact same as, where is it? If you look at all of these, where it's got all of these individual ones saying pin A through pin G set to an output, and these are all separate function calls which go and figure out what is pin A, because on an Arduino UNO using an ATMEGA 328, pin A might be a specific pin on the physical processor, and pin G might be a different, obviously is a different pin, and then pins D1, D2, D3, D4, etc. They're all separate pins. Now we don't need to worry about the D pins because we're just driving a single digit here. But these are 1, 2, 3, 4, 5, 6, 7 separate pins. I guess we'd have 8 pins if we included the decimal point, that has to be individually set up. In my code that I have now, here, we've got 2 statements. And these are writing directly to the registers of the ATMEGA 328. Now the difference is, if this would not be transferable to a different microcontroller. For instance, if you were writing code and wanting to send this out to an ESP8266, this wouldn't work because these definitions will be different. So you would have to adapt. But if you know what the process is going to be, then you can massively, I mean, you're talking in some cases hundreds of times faster coding. So this actually sets up the outputs in the state that I want them to be. Now, if you read this, it actually shows you, I actually wrote some comments here, that we're setting pins 2 to 7 as inputs, and we're leaving pin 0 and 1 as whatever they were before. We're also setting port B, pin 0 and 1 as inputs, and leaving the rest of that port alone. Now, what this represents is pin 2 to 7 of the Arduino. That's what I'm talking about here. But this is port D, bits 2, 3, 4, 5, 6, 7. Bits 0 and 1 are left alone. This is and equal. So this is the same as saying data direction register D equals data direction register D. So it would read from the register ANDed with 00000011, which effectively would set all the data direction register bits to 0 except for the last 2, or the least significant 2 bits. Same for data direction register B. That sets the zeros would set those pins as inputs, and I'm leaving them as floating high impedance. So this is the state that these displays want, is a high impedance state on the segment pins when they're not being driven to a specific charge level. A little debug statement just saying hello. And then my loop, this is counting up now, is much, much simpler. I don't have all of these massive sets of codes that are turning, doing a digital write, etc., all the way through. I've just got a int equals 0 to 10. Well, int is 0 up to 10, x++. Set the display to whatever x is, so it's going to count from 0 to 9. When it hits 10, it's going to reset. I've got my write time delay right now set to 1 second. And then if I look at the write, which is the set display, that's what I'm calling set display. That's the entire routine that's driving this display. And what I'm doing is I'm calculating the value I want, because the value array is a single byte for the whole digit, but I've got to split that up between 2 different ports. So I've taken the register D, which is port values 236, and I've shifted the digit left 2 places to avoid those least significant bits. They'll be set to a 0 initially, and then I've taken the high order 2 bits of the value that I want to output. This is from this little array up here, and I've shifted it right 6 bits, which means I only leave bits 7 and 8, sorry, bits 6 and 7 of the byte left in the register. All the other ones will be filled with zeros. I then, after I've got, that's the values that I want to output. Now you can do this in line with the actual output rate as well, but I wanted to keep it more understandable for the viewers here. The next thing I do is I change the data direction registers to output mode for the ones that I want to be outputs. So this is basically OR equals, so it's like data direction register D equals data direction register D ORed with this bit pattern. Same for data direction register B, ORed with this bit pattern. That sets all the ones to outputs, and then where I've got zeros, if they were already a 1, they'll stay as a 1 because that's the nature of an OR. You can have that one or that one equals 1, then you get a 1, right? That's what OR does. I then, little debug statement, I then literally say port D is port D, and I'm actually ANDing the port with all zeros 1 1 so that I actually initially set it to 0, but then I'm ORing it with the value from D. So I'm basically isolating the upper 6 bits and ORing it in, so I don't want to touch these lower 2 bits. And then port B, which is the port B, which is the G segment and the decimal point, I AND with the opposite because I only want to be playing around with the least significant 2 bits, and then OR it with the value I want. So again, all of these ones that are 1s, they'll stay whatever state they were in, because the AND will let them, any ones that are 1 already will stay as a 1. And then I'm ORing it with my value, which is all of these zeros up here, and then whatever these happen to be on the first and second bit for setting my value. And that's basically it. These 2 statements write all of those 8 digits. So instead of 8 write statements, I've got 2 write statements. And this is significantly faster as well, way of writing to a port, especially if you know exactly which port you're doing, but it is controller specific. You got to remember that. Then I've got a write delay, and then once I'm done, I write the port back to an input mode, so it's not driving the segment anymore, but they also set the data on that port to all zeros for the segments that I'm using. And the reason for that is because I want them to be high impedance. When by setting 0, there's no pull-up on the input. If I set these to a 1, they would have pull-ups on the input, and I don't want that. And then I do the same for data direction B. Okay, you can look in the data sheet of the ATMEGA 328 to see all this, and maybe in another video we'll do that, a little deep dive into the actual controller. Because you'll find while you're coding, once you get to a certain point in your experience level, you want to speed things up, because you'll get frustrated that you can't get more than, say, a few kilohertz out of a pin when you know the processor is running at 16 megahertz. You should be able to get, you know, a couple of megahertz out of a pin if you wanted to as a square wave. So you would have to resort to techniques like this to be able to do that. So that's what my code is. Again, I'll make that available. I need to make sure I set this to the right port. So let me just plug this in. Probably going to start doing something right away because I already uploaded the code earlier. And I'm going to compile this to make sure it's all good. Now notice I've got no libraries in this either. This is all direct coding. So you can see how simple it is to actually write to one of these displays. Okay, now I'm going to, come on, it's not finished yet. First time I was compiling this since a power up. Okay, gonna compile it again, which will be much quicker, and upload it to the chip. It's probably going to complain about the port number because I didn't set it. Yeah, it's on COM5. Port COM5. Alright, so let me just go to the zoomed in display here. So we're looking at this one right here. And I'll compile that and upload it. So there it is, just uploaded. So it's gone to 0, now it's 1. 2. Gonna zoom in anymore. There we go. That's a little better. 9, 0, 1, 2, etc. Now it's not as bright as it could be because, like I said, I'm using a divider, so I was only getting 2.5 volts instead of 3 volts. But it proves it can work. I will try and set up and do in a separate video one with, say, an ESP8266 or something like that. But the point from a coding perspective in this video is I wanted to show you how to code faster to a display, and you can take these exact same techniques to a regular 7-segment display, and it would work with it quite happily. I would have to tweak obviously this is only staying on for 1/4 of a second for the segment, but if I took out that second bit that shut off the port and left it on over time, this same technique up here of having the binary values and writing directly to the port, sorry, in here, that'll work for pretty much any port as well. So anyway, I'll leave it at that. I think you'll agree these displays are very cool. I can see a lot of uses for them, especially where you want to have an ultra thin panel of some kind, or you wanted to have them integrated into a package that requires a very, very low power consumption. If you combined a lower powered processor with sleep modes, the amount of power that these displays are taking, it would have a negligible impact on any battery. I'd imagine they would age out before they would discharge the battery. So yeah, they're pretty good. And talking about Invisible just for a moment, let me just go back to code here and bring up their website. I was having a chat with them the other day, and you know, we looked at some of these examples, as you can see here. These are being integrated into different displays, how flexible they are and things like that. They're not cheap. I mean, the kit that I have here sells for about 180 euros or thereabouts. Where is it? Buy kit. Let's have a look. Yeah, 190 euros at the moment. And that's for this kit with everything I've been demonstrating here. Now, that's a little bit expensive, but, you know, they don't want to be making all this stuff and sending it out to people that just are going to not be wasting their time. The company is interested in setting up a production and maybe making tens of thousands of displays for something. So if you were developing a product as opposed to just being a hobbyist, then, you know, if you had a specific graphical layout, and you can see, I showed you before. Let's just change my display here a second. You can see we've got a lot of different shapes, exclamations, and, you know, on-off indicators, OK, squares, bar graphs, ticks, 7-segment displays, and you can pretty much have anything. If you can, you know, basically think of it as being black and white or red, monochrome anyway, and you know, they can actually print whatever you want, but you may be wanting to be able, you know, in order for them to do that for you as a custom display, you'd probably have to be ordering, you know, a few thousand to make it cost effective, because they'd have to set up a production line, etc., etc. You can buy these individual things separately, but one of the things that I suggested to Invisible is that instead of selling this entire kit, make a production run of maybe, you know, maybe a 3-digit 7-segment display with a plus and minus and a few other useful displays, and actually make a production run and just sell some of the displays. No drivers, no wiring, no nothing, just the displays. And they may be, you know, in that case, it could quite possibly be able to make them available to the hobbyist to have a play with. You would just obviously have to use your Arduino or your ESP8266 or whatever to drive them directly. And I think a lot of people would like to be able to have access to these to play with them like that, because to be honest, you know, you're not going to use one of these boards in a production environment. All right, it's designed to be used as a prototyping environment. So, you know, you're going to create your own driver anyway. So you might as well write the code yourself. And, you know, if you can have access to some of these displays, just the display, it's going to be very inexpensive for the hobbyist and also the developer to have a look at them. And also, it means that, you know, this product gets spread around a bit more, because I think this is probably the lowest powered display module I've ever seen, and most definitely the simplest to drive. I mean, I've used e-ink displays and things like that. They're a lot more complicated to to drive. I've used these silver Sanyo displays. Their I2C interface is a little more complicated. They're like a 64 by 64 bit matrix, but more complicated to display and probably a little bit more power consumption as well. Not a lot, but it's certainly relative to this, I guess it's a lot. So, you know, this is pretty good from a, you know, I can see a lot of applications. Now, what time is it now? It is now 5:20, so that's 25 minutes. It has been since I unplugged these two displays, and you can see they've still got their display perfectly legible. So I would say that you'd be more than capable of waking your processor up, say once every 10 minutes, and maybe updating a temperature on a display, or temperature and humidity or something like that. And then going back to, you know, maybe transmit it somewhere and then go back to sleep again. And then the display would remain on for the 10-15 minutes that the processor is completely asleep. I mean, how perfect would that be? It's waterproof. You know, you put it in a panel, there's a plastic front on it. It's completely waterproof. It's fairly impact resistant as opposed to a lot of the glass displays. And you can get custom imagery. So give Invisible a shout if you're interested. I'll provide links in the description. Take the code. As I said, you can use the code for 7-segment displays with minor modifications and things like that, and all the techniques for bit driving the I/O directly that I've shown you in this video, and use it to your heart's content. Anyway, in the meantime, if you liked the video, give it a thumbs up. If you didn't, then don't. But I will see you in the next one. Bye for now.